Okay, so we're talking about the magnetic forces on charged particles. Okay, and we're trying to apply the right-hand rule, the third right-hand rule. Remembering that we have three right-hand rules. The third right-hand rule, to try to identify the direction of the force that's being applied on a charged particle that's moving across a magnetic field. And we also know that the force that's going to be exerted on this charge is going to be directly proportional to the magnitude of the charge, the velocity or the speed it's going, or it has, the magnetic field, which is called B, and the angle that the magnetic field, the sign of the angle that the magnetic field has with regards to the velocity vector. And the right-hand rule tells us that if the magnetic field is going in one direction, and that's going to be indicated by these fingers here, and the velocity vector is going to be our index finger, then our thumb is going to indicate the direction of the velocity. Now, if the charged particle is positive, then the thumb indicates the direction of the velocity, of the force, of the force. The thumb indicates the direction of the force. Index is velocity, the rest of the fingers is the magnetic field. If the charge is positive, the thumb indicates the direction of the force. If the charge is negative, then the force is going opposite of the thumb. So let's look at these problems here. So this is just kind of an overview of what we're talking about. And so let's look at the first problem. The calculation of the force is very direct. It's just going to be Q, which in this case is 5 microcoulombs multiplied by the velocity, which is 15 times 10 to the 3 meters per second. The magnetic field, remember it's given in Teslas, 0.25 Teslas, and the angle it has is 65 degrees. So boom, 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 sine of 65, we should get 1.699 or 1.7 approximately times 10 to the minus 2 newtons. Now, where is this force going? Well, again, looking at the page, our index finger is going in the direction of is going in the direction of the it's going in the direction of the velocity. Okay, the other fingers are going in the direction of the field. And the thumb, in this case, is going, right now, the way I'm showing it, it's going into the screen or into the page, okay? It's going into the screen or into the page. And so that means that the force is going into the paper. It's going into the page, in this case, or right now into the screen. It's going into the screen, the way I'm looking at it. When I was in the breakouts, we were trying to do that, but it might be confusing because, again, you're looking at your page and I'm trying to do the right-hand rule, but you're looking at the video, so the mirroring can affect or confuse that. So if you do your right-hand rule the way this image is, I was actually in the break, I was actually taking pictures of my hand and pasting them here. The force is going to be going into the page. And just to represent that, I'm using here a little circle. The circle to represent it's going, oh, actually, it should be, if it's going into the paper, let me correct that. If it's going into the paper, it should be, yeah, if it's going into the paper, I'm sorry, I made a mistake here. So I can make mistakes. Of course we can. If it's going into the paper, it should be across. Okay, so just give me a moment here to correct that. It's going into the paper, it is across. It's going out of the paper, it's going to be if it's going out of the paper, it's going to be a circle. Okay, so let me do a quick correction here. Apologies for that. Okay. Do it quickly. And this is live for anybody who's seeing these videos. So this is an edited video, so it's live, so mistakes can be made. So apologies for that. And if you don't like it, then you may watch. I'm not talking to you guys. You guys are my students, but if somebody's watching this video and doesn't like it, they can watch something else on YouTube. And again, for the person who commented on my video, the VOM about the, well, sorry, I have allergies. A lot of people have allergies, okay? So if you do not like me going like this, well, sorry, I'm gonna be doing that a lot in my videos because I have allergies. Tough. Go watch other videos. And so I'm sorry about that. Again, the image is like this. So the thumb is going into the page. So this is the little cross indicating that it's going into the page. I'm going to be going through them, and if you have questions, let me know. But again, for when you're reviewing this, try to put your hand like the hand that's in the image of the PowerPoint. This is going to be uploaded to Blackboard. Okay. In the next one, it's a very similar situation. The only difference with this one is that the charge is negative. What happens with the charge is negative? So the field is going downwards. The velocity is going upwards at an angle, and the thumb is still pointing into the page. However, since the charge is negative, then the force is going to be going opposite the way the thumb is. So it's actually going to be going towards us. So whenever the charge is negative, it's the opposite of where the thumb is going. And the calculation, again, it's 3 microcoulombs times 6 times 10 to the 3 meters per second times the magnetic field, which is 0.25 Teslas, and the angle. Remember, if you have any questions, stop. Now for the next one, now the magnetic field has little crosses. That means the magnetic field is going into the page. So the magnetic field is going into the page. These are going into the page, okay? Into the page. I'm looking at my hand here. Yeah. So it's going into the page. Oh, I have to do it. I have to do it the way I'm looking at it here. So I'm sorry. It's going into the page. Okay. No, I'm sorry, like this. It's going into the page, and the finger is pointing outwards. Okay, because the velocity is going outwards, and therefore the thumb points upwards in this direction, which is the force that's indicated here. Let me also do a quick adjustment here. I'm sorry. We're actually talking about the force or the thumb. Okay, so that's actually the vector. It's the thumb that we're looking at. Okay, it's the thumb that we're looking at. And so the thumb is pointing outwards. That means that the force is going outwards. Okay, it's going outwards in the direction that we have this vector here. Okay, again, do your hand the way, looking at the page, put your hand the way you're seeing it in the image, and that's going to give you the direction of the force. And the calculation again is done directly. For the next one, it's a very similar situation. However, now the field is also going inwards. The velocity vector is the index finger. It's going downwards. In this case, your thumb is going to be pointing upwards. However, the charge is negative, so the velocity vector goes opposing the thumb, and so that means it's going downwards, the way it's indicated here in the way it's indicated here in the image. Okay. Okay. Questions up to this point before we move along? Again, I'm putting the images there, so when you look at it, try to put your hand the way it's in the image, and that's going to give you the relationship or the direction. Okay. Now, for this one, or in this case, And so for this one, now the dots indicate that the magnetic field is going out of the page. Okay, the magnetic field is going out of the page. The velocity vector is going to be the index finger. It's the red arrow. And so the thumb is going to be pointing downwards. That's the blue arrow. That's going to be the force. Okay, it's going to be pointing downwards. Calculation is direct. Okay. In this case, in this particular case, just notice that the angle that was given, it didn't give us the angle, but it was indicating here in the image that the angle was 90 degrees. Okay, so the angle would be 90 degrees. And lastly, for this one, again, the magnetic field is going towards us because it's the low points. It's going towards us. The index finger is going to be indicating the velocity. And so the thumb indicates the force, but the charge is negative. So instead of going towards the thumb, it's going away from it. Okay. That's basically the way we configure the right-hand rule. Okay. So when you're reviewing these problems, remember, use the right-hand rule and try to place your right hand the way it's in the images. And that's going to give you the reasoning to indicate or be able to identify the different vectors and do the calculations for identify where the force is going. Yes, Omar, go ahead. You have a question.
Yes, I have a question. My question is that in the calculations, we use the 90 degrees instead of the 40 degrees that are placed in the diagram. So why do we do that?
Yeah, that's a good question. Both problems C and D, and actually all of the problems where the field is going inwards or outwards and the velocity has a vector, in all of them, notice that they're not providing an angle here, and they're giving an angle they're giving an angle in the diagram, but they're not providing an angle in the data. And you calculate with 90 degrees. Why is that? We kind of have to visualize things in 3D. Okay. And try to do this. Let me grab two pencils to see if I can do that and do it. It'll probably explain a little bit better than doing it with my hand. So I've got a pen here. Give me a moment. Let me get another pen. Let's see if I can explain this. I'm going to try to explain this. These explanations in Zoom, this is new. The 3D thing in Zoom is interesting. Okay, Omar. So imagine this and try to grab two pencils to do that. The magnetic field is this long. I think this is a pencil or something. Okay, are we okay up to this point, Omar? This is the magnetic field. And the magnetic field is going like this. Let's say that it's going outwards. Okay, are we okay up to this point? Right? And then I've got the velocity that's going like this at an angle. Are we okay up to this point, Omar, and the rest of you? You see this?
Yes.
So this is going in here, and then we've got this here at an angle, right? We okay up to this point? Omar, regardless of how I move this, which is the blue pen, regardless of how I move this vector, what is the angle with regards to the vector, to the velocity vector and the magnetic field vector? So regardless of if I do this, what is going to be the angle with regard of the velocity vector with the magnetic field vector? It's this angle.
Yeah, 90 degrees.
It's going to be 90 degrees. So actually the degrees that are placed in the problem, it's kind of like the degrees that are placed here, these are kind of purposely placed there just to generate a bit of confusion. So I hope everybody sees this. So again, and I'm gonna rotate it now like this. I'm gonna give you another perspective. So I was doing this. Now I'm gonna give you this perspective. This is the magnetic field vector, the darker one, and the pen, the blue pen, is the velocity vector. So I was doing this right now. Okay, everybody see that? I was doing this. This is the velocity vector that has an angle with regards to the plane. Now I'm going to give you another perspective. Let's look at it like this. And when I'm moving this, what is the angle between the two pens? Is it clear to everybody that it's 90 degrees? You see that?
Yes.
So in cases C, D, E, and F, regardless of what is the angle, regardless of the angle that the velocity has, the angle that it's having with regards to the field in that case, in these cases in particular, is going to be 90 degrees. Okay. In the other cases, the field was going this way and the velocity was going this way. Well, we do have an angle there. Or in the other one that the field is going this way and the velocity is going this way, we do have an angle. It's always it always has to be the angle that we're considering. It's the angle that we have with regards to the magnetic field and the velocity vector. Okay. But if I'm looking at it in three like this, then the angle between the velocity vector and the magnetic field vector is going to be 90 degrees. Okay, so this is just kind of like a thing to kind of catch you off guard. Was that clear, Omar?
Yes, it was clear.
Yeah. So,
thank you.
Thank you, Omar. Okay. Questions with this before we close up? Any additional? That's a good question, Omar. That was a good question. Any additional questions?
No questions, Professor.